So far, we've talked about some key characteristics of every parabola, like the y-intercept, the vertex, the axis of symmetry, but something equally important to talk about are maximum and minimum values. One thing I clipped from the book here to the left side is this little bubble that says, watch out, the terms minimum point and minimum value are not interchangeable. And this is something that people are very guilty of using interchangeably. The minimum point is the vertex when the parabola opens up. The maximum point is the vertex when the parabola opens down, when the leading coefficient is negative. But the value, that's different. The value is going to literally just be the y-coordinate. The y-coordinate is the minimum value, and the y-coordinate is the maximum value. So if it's asking for a value, it wants just one number, not a point with two coordinates, but one number, and that one number is the y-coordinate. Looking back at this key concept box, if your quadratic equation has a leading coefficient that's positive, the parabola opens up. If the leading coefficient is negative, it flips upside down and the parabola opens down. Let's look at the domain. If we look at the domain, we have graph above us, graph above us, graph below us, graph below us, graph above us, everywhere. Same with this one. There's graph below us, graph above us, graph below us. So when we're talking about domain, no matter if it opens up or down, the domain is going to be from negative infinity to infinity. It's going to be all real numbers for all of our quadratics. Now let's look at the range. For this particular quadratic, when a is positive, it opens up. I have graph here, to the left and right, to the left and right, to the left and right. For here, my domain, or excuse me, my range, I misspoke, my range is going to come from this point. I have to erase that. It's going to come from this point right here, this y value, and it's going to go up to infinity. When the graph opens down, however, it starts at negative infinity and goes up to that point. So that's going to look a little different. So the range is going to be from negative infinity up to that value. So you can see that the domain is the same for both of them, no matter if the graph opens up or down. Those are the only two ways the graph can open. It's not going to open to the left or the right. When it opens up, it's going to go from that value, that minimum value, to infinity. When it opens down, it's going from negative infinity up to that y maximum value. Let's try an actual problem here. Does this have a maximum or minimum? Well, the first thing we're going to do is look at the sign of the leading coefficient. It's negative, which means it's going to open down. I'm not even going to graph it. I'm just going to picture in my mind that it opens down. So this vertex is going to be a maximum. It's going to have a maximum value. I can tell that just looking at the equation. Now, what is that maximum? Well, it's going to be the vertex, the y value of the vertex. So think about how we find the vertex. We need to do negative b over 2a, which gives us the x component. And then we have to plug that back into our function to get the y value. So let's try it. This is A, this is B, this is C. The opposite the opposite of B over 2 times A. And then I have to plug it back in to get my Y value. So my X value is negative 12 over negative, reducing negative 12 over negative 8 becomes positive 12 over positive 8. Dividing them both by 4, we get 3/2. Now we probably don't want to use mental math to substitute this fraction, even though we could. Let's use our calculator. I'm going to take 3/2, 3 divided by 2. I'm going to store that for x. Then I'm going to type my function, negative 4x squared plus 12x plus 18. Slide my screen over a little bit so you can see better. It equals 27. So my maximum value is 27. The maximum point is 3/2, 27. Now we need to talk about the domain and the range. The domain is our favorite part. It's all real numbers. The range, since it opens down, down goes to negative infinity, and it's going to go all the way up until it hits 27, including 27, so we change that to a hard bracket. Eddie is organizing a charity tournament. He plans to charge a $20 entry fee for each of the 80 players. So when you think about that, 20 times 80, $20 for 80 people would be $1,600. And that's right here where our graph starts. That's the point 0, 1,600. He decided that he thinks he could make a little bit more money by raising the entry fee, though, by $5. But when he does that, 5 fewer people entered. But he still made more money, even with a few less people entering. That was after 1 increase. After 2 increases, he made more money. 3 increases, he made more money. 4 increases, he made more money. All the way up until he got to about 6 increases. And then it wasn't worth it. He was charging too much. People weren't wanting to play and enter into this tournament. So he wants to know, what's the maximum? How much should he charge to maximize the charity income? We can see from our graph here that the maximum is going to be right here. That's the highest. He made more money, he made more money, he made more money, and then he started to make less money, less money, less money, all the way until he made nothing if he increased the price 16 times. So let's structure an equation, a quadratic equation, model this situation. If we think about it, we take the number of players times the entry fee. And that's how we get the total amount that he makes. Well, if the number of players is 80, but he loses 5 players every time he increases, that's our X, the number of increases. And his entry fee starts out at 20, but it goes up $5 every time he increases. Let's multiply this out. You can use the box method or FOIL it, whichever you prefer. We'd have 80 minus 5x, 20 plus 5x. That gives us 1,600 minus 100x, 400x minus 25x squared. So I could model this in standard form as negative 25x squared plus 300x plus 1,600. If I were to graph this, it would look just like this picture we have on the right. So again, I want this number. It's kind of hard to tell from the graph. It looks like it's at 6. So I think that's what my X value is going to be, but I don't want to assume things. Let's make sure. let's figure out the vertex, which remember we can find by doing negative b over 2a and then running that back through the function to get the y value. So negative 300 over 2 times negative 25, negative 300 over negative 50, simplifying, we get 6. So we were right. There were 6 increases. Well, how much would he be charging if he increased it by $5 6 times? Well, 20 plus 6 $5 increases, that's 30. He's charging $50 to enter. How many people would be willing to pay that? Well, let's take our 6 and plug it back into our original problem. And again, given the nature of the numbers we're dealing with, sometimes it's easier to simply use our calculator. 6 stored to x, negative 25x squared plus 300x plus 1600 gives me 2500. So if he charges $50 per person, he will bring in $2,500 if he has 6 price increases. That is how he should maximize his prize pool.